Good afternoon to all of you. Now we are going to talk about thermal remote sensing. I am Dr. Shashi Kumar, faculty in photogrammetry and remote sensing department of Indian Institute of Remote Sensing. So in next 1 hour we will be discussing on thermal remote sensing. So when we are talking about thermal infrared remote sensing, so thermal infrared energy is emitted from all objects that have a temperature greater than the absolute zero. It means that all the objects having the temperature more than the absolute zero temperature or greater than the absolute temperature, they all are going to emit the thermal infrared. Now the sensors, they are going to capture the emitted energy of the thermal infrared, and finally those energy information which has been captured, that is converted into the temperature information to get the temperature value. When we are talking about the remote sensing, so in remote sensing you can see that there are several remote sensing techniques. Mainly we are categorizing in optical multispectral, which is using the visible and the reflected infrared range of the electromagnetic spectrum. Then we are talking about the thermal infrared, where we are talking about the emitted energy, and that is mainly ranging from 3 micrometer to 14 micrometer. Sometimes people are also using till 20 micrometer. And when we are talking about the microwave remote sensing, so the wavelength range will be 1 millimeter to 100 centimeter. Now the interesting thing is, sensors are designed to capture the different phenomena of the electromagnetic wave used in the different portions of the electromagnetic spectrum. Like in the case of optical multispectral, you know that we are using the visible range, that is covering 0.4 micrometer to 0.7 micrometer, and the reflected infrared, that is 0.7 micrometer to 3 micrometer. Now this portion is having the property in which we are using the reflection of the light or reflection of the electromagnetic wave in this wave in this range. So the sensors are designed to capture the reflected energy. Now when we are coming to microwave remote sensing, the spectrum, electromagnetic spectrum for microwave is 1 millimeter to 100 centimeter. There we are talking about the back scattered portion of the energy. There we are talking about the scattering phenomena of the electromagnetic wave, and the sensors are capturing, the microwave sensors are capturing the back scattered portion of the electromagnetic wave or the back scattered energy. So, and based on that the information extraction is done. Similarly, in the case of thermal remote sensing, there is a entirely different property of the electromagnetic wave. Here we will be talking about the emitted energy. So in optical multispectral, reflected, microwave is scattered or back scattered, and in the case of thermal remote sensing, this is emitted energy. Now, so when we are talking about the emitted energy, so we should know that which object is going to emit the energy. So here in the first line it is written that all the objects having the temperature greater than the absolute zero, means all the objects in such an environment where we are going to get the temperature greater than absolute zero, all the objects, they are going to emit the energy. Now here if you will talk about the landscape, so in the landscape we are going to talk about the different features like or the different objects, planetary objects, as well as when we are talking about Earth surface, different features like vegetation, soil, rock, water, they all are emitting the thermal infrared. Since our eyes are not sensitive to the thermal infrared, but the sensors could be designed to detect the thermal infrared, because our eyes or human eyes are mainly sensitive to the visible range, that is 0.4 micrometer to 0.7 micrometer. Now this image is showing the color composite image of La Palma lava flow. So in this image, Sentinel-2 data set has been used. Though the thermal band has not been used, but reflected infrared has been used. Here you can see that when reflected infrared has been used in generating the color composite, the lava flow direction and lava flow, you will be able to clearly detect. Now this is another image in which we are going to see the comparison of volcanic eruption of Hawaii Island in the two images. One is a microwave image, another is the combination of optical and the thermal bands. Now here you can see that in the right hand side image, first of all we should know that the thermal data sets that will be mainly capturing the thermally emitted energy or the thermal emission. It means that the location where temperature will be very high, thermal emission will be very high. So those locations are going to appear very, very bright. Now in the optical multispectral data set, what we are getting that the atmospheric or you can say the atmosphere is filled here with some cloud portion as well as some haze and some kind of foggy information is there. We are not clearly able to detect the clear feature on the earth surface. But when the Landsat 8 band number 10 was used in the color composite image with in addition with the sentinel data set. So here we are able to clearly see the lava flow direction of Hawaii Island. Similarly, now sometimes it is also happening like due to the gaseous eruptions during the volcanic eruption. Sometimes we are going to see the gaseous eruptions, and when the dust particle and the gaseous particles will be very dense, at that time we are not going to get the exact information of the surface. So at that time SAR data set is also used. Here you can see that one SAR data set is there, and very clear information of the lava flow could be easily seen here. Now the main purpose of the thermal data set to detect the thermal properties, mainly temperature, as well as the thermal properties to characterize the geo and biophysical characterization of the objects. So here you can see that left side image is the image which was acquired on January 6, 2002. That is the ASTER nighttime thermal infrared image for Chile volcano, for a volcano in Chile. And the right side image is the daytime image that was acquired on November 10, 2000. And here you can see that the blue, green and red bands were used. True color composite image is generated. Now from the true color composite image or the color composite image that is shown in the right side, we are able to clearly get the information of the object, and from the interpretation one can say that okay, now this is a volcanic crater because crater could be easily seen here. Crater rim is also visible. Crater is seen here, and one can say that okay, now this is the volcanic crater. But since there is no active eruption, no active gaseous or the volcanic eruption or the lava flow from this volcano, so we cannot say that without seeing any gaseous or the lava flow eruption, we will not be able to say that whether this volcano is active or still active or dead. But when the thermal data set is having coarser resolution in comparison to the optical multispectral. So when the thermal data set was acquired for the same area, now here what we are going to see, we are seeing that the center, from the center of the crater, we are going to see very high energy because this is appearing in bright. In the thermal imagery, any location where we are going to see the bright patches, it means that for those locations, the very high thermal emission has been sensed. It means that in those locations temperature may be very, very high. So here the we are getting the bright patch. It means that the temperature is very, very high for this location. So now from the after analyzing the thermal data set, one can say that this is not a dead volcano. This is still active volcano, but it is active volcano without any gaseous or the gaseous eruptions or without any lava flow. So by seeing that one can see, and other features here you can see that like the mountainous region. Here you can see that you are going to see, if you will analyze this. So here we are going to see that the presence of very less temperature. It means that very less temperature or very less thermal emission is detected. It means that temperature in this location is very, very, very low. Now again, if you will move outside, so here what we are going to see, very high thermal emission. Or you can say moderately high thermal emission. So here we are going to see the moderately high thermal emission. It means that the high temperature is sensed for this location. So thermal data sets are also used for characterization of land use, land cover, as well as characterization of the geo and biophysical parameter of the geological features or the forest area. For different kind of features, they will have different kind of thermal properties. So thermal data sets are also used in the interpretation of thermal properties of those features or objects. This is airborne thermal data sets which is acquired in the daytime. So left hand side image is showing the true color composite image, and the right hand side image is showing the color composite image that is generated using the thermal data set. Now in the thermal data sets, what we are going to see that yellow and red areas, these areas are hot, and hot features you are going to see from the roads as well as from the buildings. From building top of the building and other from the other features, we are going to see that a very high temperature is detected. Now blue and green, if you are going to see, so these are showing the cool temperature, and they are mainly indicating the water and vegetation. So if you will see that water, this is appearing the dark blue color, and the vegetation is also appearing in the blue color in the imagery. So if you according to the information which is retrieved, the bright and the red areas in this image, they are having the temperature approximately of the 65 degree centigrade, that is 149 degree Fahrenheit, and the dark green and blue areas are 25 degree centigrade. Now here you can see that due to the presence of vegetation, you can see that the locations without vegetations or the buildings and roads, they are showing the temperature near to 65 degree, but the locations which are having the vegetations, they are showing the temperature near to 25 degrees. So you can see that there is approximately in daytime 40 degree variation is there in detecting the temperature. Now when we are talking about the thermal infrared remote sensing, so this is carried out in the thermal range of the electromagnetic spectrum, and the thermal range is 3 micrometer to 14 micrometer, because if you will see, so 0.7 micrometer to 1.3 micrometer, this is the reflected infrared, this is the near infrared, and mid-red infrared is 1.3 to 3 micrometer, that is again reflected infrared used with the optical multispectral remote sensing. The thermal infrared or the emitted infrared is 3 to 14 micrometer, and this is showing this portion of the electromagnetic spectrum. Now when we are talking about the range of the electromagnetic spectrum which is used in thermal remote sensing, so this is 3 to 14 or 3 to 20 micrometer, but not the entire range is used for the remote sensing, for the earth observation, because there is absorption band from 5 micrometer to 8 micrometer. So only 3 micrometer to 3 micrometer to 5 micrometer and 8 to 14 micrometer, these two ranges are used in the earth observation, because 5 to 8 micrometer is the absorption band. All the infrared information in 5 micrometer to 8 micrometer is absorbed by the atmospheric water vapor. Now sometimes people are asking what is the difference in thermal infrared and the infrared which is used with the optical multispectral. So the main difference between thermal infrared and near infrared is that thermal infrared is emitted energy, whereas the near infrared is reflected energy similar to the visible light. Now when we are talking about the thermal remote sensing, so these are the important terminologies which are used in thermal remote sensing, like kinetic heat, kinetic temperature, radiant heat, radiant energy, and radiant temperature and radiant flux. So these things are written here. So the energy of particles of matter in random motion is called the kinetic heat, or you can also say that the heat which is coming due to the internal motion of the particle, that is known as the kinetic heat, or it is also referred as the kinetic heat, or kinetic heat is also referred as the internal heat. All the objects having a temperature above absolute zero. Absolute zero is also in degree centigrade. If you convert, this will become minus 273.16 degree centigrade, and in Fahrenheit it will be minus 459.69 degree Fahrenheit. So all the objects above absolute zero exhibit this random motion. When these particles collide, they change their energy state and emit electromagnetic radiation. As we have talked previously, like all the objects above absolute zero, they are going to emit thermal radiation. Now, the amount of heat can be measured in calories. The calorie is the amount of heat required to raise the temperature of 1 degree of water by 1 degree centigrade. 1 gram of water by 1 degree centigrade. Now, we can measure the true kinetic temperature or concentration of this heat using a thermometer, because generally we are using the thermometer to measure the temperature. Even like for the body temperature also we are using thermometer to measure the temperature. So by making the contact with the objects using the thermometer, one will be able to measure the temperature. We perform this in situ temperature when we are ill. So we can also measure the true kinetic internal temperature of soil or water by physically touching them with a thermometer. Now, fortunately for us, an object's internal kinetic heat is also converted to the radiant energy, because there is a strong relation with kinetic energy and the radiant energy. The electromagnetic radiation exiting an object is called the radiant flux and is measured in the watts. The concentration of the amount of radiant flux exiting an object is its radiant temperature. So, the radiant temperature is measured with the help of the radiometer or the thermometer, which is placed above the object, or like in the earth observations, sensors are placed to measure the radiant temperature. So, radiant temperature is measured by the sensors, and there is a strong relation between radiant temperature and the kinetic temperature. When the radiant temperature is measured, by knowing the emissivity, one will be able to measure the kinetic temperature. In the next few slides, we will be able to see what is that relation. There is usually a high positive correlation between the true kinetic temperature of an object and the amount of radiant flux radiated from the object. The same thing we were talking, the relation between the kinetic temperature and the radiant temperature. So, we can utilize the radiometers placed some distance from the object to measure the radiant temperature. Now, when the radiant temperature is measured, by using the correlation, one will be able to find out the kinetic temperature. Now, when we are going to see, so if we are saying that okay, there is a linear relation, so no, there is no really linear relation between the radiant and kinetic temperature. They are mainly governed by the emissivity. So, when the emissivity will be known, one can measure, but the relation is not the linear. Now, this is the atmospheric window in the electromagnetic spectrum in which the remote sensing is carried out. The visible range 0.4 to 0.7 micrometer, then the reflective infrared 0.7 micrometer to 3 micrometer, then 3 to 14 micrometer. Now, here you can see that there are several absorption bands also, but mainly we are going to talk about the absorption band particularly here in the thermal. So, in the thermal it is 5 micrometer to 8 micrometer is the absorption, mainly sensitivity is there due to the H2O. So, we can get the information. So, in this 5 to 8 micrometer we cannot get any information of the earth object due to the absorption of the thermal infrared due to the water vapor. Now, we are going to talk about some basic laws which are used in the thermal remote sensing. So, here the first law which we are going to talk, that is the Planck's law of black body radiation. So, Planck's black body radiation law describes the electromagnetic radiation emitted from black body at a certain wavelength as a function of its absolute temperature. So, here you can see that spectral radiant excitance that will be equals to 2 pi hc square, where h is the Planck's constant, c is the speed of light, divided by lambda to the power 5, because here we are because the spectral radiant existence will be depending on the wavelength also. Okay. So, because here it is mentioned black body at a certain wavelength. So, here the wavelength is represented by lambda. So, lambda to the power 5 and then e to the power hc divided by lambda kt, where T is the absolute temperature and K is the Boltzmann constant. So by using that, when the black body curve will be plotted, so this will be the type of the black body curve that is shown here. The total energy a black body radiates and the wavelength of the maximum emittance depends on the temperature of the black body and can be described by the Stephen Boltzmann law and the Wien's law, because these laws are mainly derived from the black body Planck's law of black body radiation. Now, black body radiation curves at different selected temperatures. The laws of the Planck, Stephen Boltzmann, and the Wien's displacement law are depicted in this figure. So here you can see that Stephen Boltzmann. So this is the marked area under 300 Kelvin, and the Wien's displacement law. The green dotted lines, these are shown here. The blue bar indicates the blue bar is indicating the visible range. Okay, and the green dotted line, that is showing the Wien's that is derived from the Wien's displacement law, and this area is showing the Stephen Boltzmann law. This is mainly derived from the Stephen Boltzmann law. Now then we are going to talk about the Wien's displacement law. Now this law talks about the relationship between the true temperature of a black body in degree Kelvin and its peak spectral existence or the dominant wavelength. So if you will see, so dominant wavelength lambda max will be equals to k divided by T, where k is constant, that is 2898 micrometer degree Kelvin, and T is the temperature in degree Kelvin. So when you will have the information of the temperature in degree Kelvin of any object, so you can find out the dominant wavelength. Now when you can find out the dominant wavelength, you can find out the suitable sensor, or you can find out the suitable wavelength in which the sensor could be designed to find out the desired information. Like here, if you will see the dominant wavelength for the Earth observation. So here you can see that as from the relation is 2898 divided by T for the lambda max. Now if you will see that the Earth's average temperature is 300 degree Kelvin or 80 degree Fahrenheit. So when 300 degree Kelvin will put, so dominant wavelength will come 9.67 centimeter. So here when we are getting 9.67 centimeter as a dominant wavelength for the Earth surface, it means that we should always select the wavelength towards the or near to the 10 micrometer for the Earth observation, because the dominant wavelength is 9.67 centimeter. So generally for the Earth observation, if you will see, so most of the sensors for the Earth observation, to find out the geophysical properties based on the geophysical characterization based on the thermal properties of the objects, most of the sensors, they are designed in the wavelength range in between 8 to 14 or mainly near to the 10 micrometer. Why? Because the wavelength, the dominant wavelength for the Earth surface is 9.67. Similarly, you can also find out, try by yourself, you can find out the dominant wavelength for the sun or dominant wavelength for different kind of features. Like here, what we try to do, suppose we have the information of the forest fire for which the temperature is approximately 800 degree Kelvin. Now when the temperature is approximately 800 degree Kelvin, so if you calculate the dominant wavelength, so this will be coming nearly to 3.62 micrometer. It means that for doing the observation of the forest fire, suppose I want to use the drone system to detect the temperature information or to find out the most fruitful information or the most desired information for the forest fire, at that time we should always design a thermal sensor which could acquire the data set in 3 to 5 micrometer. Okay, and the same thing as we have discussed for 300 degree Kelvin, the dominant wavelength is 9.66. So thermal infrared detectors for Earth observation, they are mainly designed in 8 to 14 micrometer region of the electromagnetic spectrum, because they are the most suitable or the most appropriate. Now we are going to talk about the Stephen Boltzmann law. So this law tells about the information of the energy, how the energy will be calculated as a function of temperature. So this law is derived by integrating the Planck function with respect to wavelength. So here you can see that it shows that the energy or the radiant flux will be equals to sigma, that is the Stephen Boltzmann constant, multiplied by the fourth power of the temperature. So if we have the information of the temperature, we can also calculate the energy or the radiant flux by putting the by multiplying the fourth power of the temperature with the Stephen Boltzmann constant. Now we have learned about the basics of thermal remote sensing, basic concept. So we know that the thermal remote sensing is mainly working with the concept of the kinetic temperature, that is the internal temperature, and the radiant temperature. So the radiant temperature is measured with after knowing the kinetic temperature, or when the radiant temperature is known, kinetic temperature could be measured. Now how to measure that, how to measure these temperatures? So here there is a relation. So radiant temperature will be equals to 1 by 4th power of the surface emissivity multiplied by the kinetic temperature. So this radiant temperature could be measured by the radiometer or the thermal sensor. Thermal sensors are measuring this information, the radiated energy or the emitted energy. Those are measured by the sensor, or or you can say the energy or the temperature which is sensed by the thermal sensor will be the radiant energy or the radiant temperature. Now once the radiant temperature is measured, and if we have the information of emissivity of the surface, then we can easily measure the kinetic temperature. Now this slide shows the emissivity of the surface. Even this is that if the two objects, they are having the same kinetic temperature or the same internal temperature, but they may have the different radiant temperature. Why? Because here we know that the radiant temperature is depending on the emissivity of the surface. So when the emissivity of the surface will be low, like here one aluminum block has been considered here, in the kinetic temperature of this aluminum block is approximately 288 degree Kelvin, that is 15 degree centigrade. Now half of the portion of the aluminum block is polished by the polished shiny surface, and the half of the portion is painted by the black carbon particle. Now here you can see that the emissivity of the shiny surface is approximately 0.05, and emissivity of the black carbon particle, this is 0.98. Now what we can see that when we are going to measure the radiant temperature, so radiant temperature will be equals to 1 by 4th power of emissivity, that is 0.05 raised to power 1 by 4 or raised to power 0.25 multiplied by 288. So for this surface, shiny surface, the detected radiant temperature by radiometer is 136.2 degree Kelvin. Now for the same material, if the surface emissivity is changed, now surface emissivity is close to 1, this is 0.98, then here we can see that the radiant temperature is, detected radiant temperature is near to the kinetic temperature, because in this case radiant temperature become 286.5 degree Kelvin and the kinetic temperature is 288 degree Kelvin. It means that emissivity is a governing factor for the thermal emission. So now we should know something about the emissivity also. So for the black body, emissivity is 1. So here emissivity, when we are talking about emissivity is basically a ratio, and this ratio is the ratio between the radiant flux exiting a real world selective radiating body and a black body at the same temperature. So here we know that the radiant flux exiting from a body, that will be less than the black body. So the emissivity, if the gray body will be able to emit the radiant flux in the same amount as of the black body, then the emissivity will become 1. It means that gray body is black body. But for all the objects in reality, or in the real world scenario, all the objects, they will have the emissivity greater than 0 but less than 1. The same thing is written, all the objects, they will have the emissivity ranging between 0 to 1. Okay. Now, some materials like distilled water, they have the emissivities close to 1, like 0.99 over the wavelength interval from 8 to 14 micrometer. And like polished metallic object like the polished aluminum, this will have the emissivity 0.08 or sometimes less than this. And the stainless steel, this will have the 0.16. So, all the metallic objects, they will have the very low emissivity, and water and the black carbon particle, they will have the very, very high emissivity. Now, as we have seen that the two objects, when they are having the same kinetic temperature, but due to the change in the emissivity of the surface, because here we are not talking about the emissivity of the object, we are talking about the emissivity of the surface, because emissivity is completely depending on the surface. So, due to the change in the emissivity, there was the change in the radiant temperature. So, now here we are going to talk about what are the factors which are influencing the emissivity. So, these factors, these factors are listed here. So, first one is color. So, darker color objects are usually better absorbers, and when they are better absorbers, they will be good emitters. And if they are good emitters, it means that they will have the high emissivity. And the light color objects or the bright colors, they will have the less emissivity, because there will be more reflection of the incident energy than the absorption. So, that when the any object will be reflecting more, so it means that absorption will be less. When absorption is less, then emissivity will also be less, because emissivity is depending on the absorptance. Now, surface roughness. So, when the surface roughness will be increasing, so the emissivity is also going to increase. The greater the surface roughness of an object related to the size of the incident radiation, the greater the surface area of the object and potential for absorption and re-emission of the energy. It means that when the surface roughness will be increasing, emissivity is also going to increase. Now, here we are talking about this point is the moisture content. So, when the moisture content will be increasing or the moisture will be increasing in the object, so the object will have the more potential to absorb the energy, and finally it will be a good emitter. So that when you will compare the wet soil and dry soil, so the moisture content in wet soil will be more, so that they will have better emissivity in comparison to the dry soil. Now, field of view, that is also very important to calculate the emissivity, because the emissivity of a single leaf measured with a very high resolution thermal radiometer will have different emissivity than an entire tree crown viewed using the coarse spatial resolution radiometer, because here the when we are talking about the emissivity of single leaf, that will be different than the emissivity of the entire crown. So, it also depends on your resolution and the field of view. Now, when we are talking about the wavelength, so the emissivity of an object is generally considered to be the wavelength dependent. Here, because example is given, while the emissivity of an object is often considered to be constant throughout the 8 to 14 micrometer regions. Do not read as millimeter, this is micrometer region. And the emissivity may be different in the 3 to 5 micrometer region. Now, viewing angle of the camera. So, with the when the viewing angle of the camera will be changing, so different emissivity will be difference in the emissivity may be detected or the absorbed. Now, when we are talking about the interaction of thermal radiation with the terrain element, so when we are talking about the incoming radiation, so incoming radiation will be distributed when any electromagnetic wave will incident on the surface. So, as you can observe here in your observation, for your observation, it is shown here that the incident radiation is divided in three parts. One portion will be absorbed by the surface, some portion will be transmitted, and some portion will be reflected. It means that the incident radiation, when we are talking about the incident radiation, if this is represented by incident energy represented by EI, so EI will be sum of absorbed energy, reflected energy and the transmitted energy. Okay. Now when we are going to divide it by EI, so what will we are going to see? We are going to see the ratio between the absorbed energy and incident energy, reflected energy and the incident energy, transmitted energy and the incident energy. So what we are going to see, that EI divided by EI, this will become 1, and EA divided by EI. So this will be the absorptance. This is going to tell that this is going to tell the potential of the surface to absorb the incoming radiation. So this will be the absorptance. The ratio between the absorbed energy and the incident energy is going to tell us the absorptance of the surface. Now when we are coming to ER divided by EI, this is the ratio between the reflected energy and incident energy. So this is known as the reflectance, because this is going to tell the potential of or the capability of the surface to reflect the incoming radiation. Now another one is the transmittance. So this is going to tell about the potential of the surface to transmit the incoming radiation. So this is the ratio between transmitted energy and the incident energy. So that if you will see, the absorptance plus reflectance plus transmittance, that will be equal to 1. Now we know that the reflectance plus transmittance plus absorptance will be equal to 1. So and what will happen according to Kirchhoff's law radiation, the absorptance will be equal to the emissivity. The Kirchhoff's law radiation states that the spectral emissivity of an object equal to its spectral absorptance, so that good absorbers are good emitters. So now here the absorptance is replaced, absorptance alpha is replaced by the emissivity E. So now the relation is E plus rho plus tau is equals to 1. Now what is happening, like when we are talking about the remote sensing, so most of the objects appearing on the earth surface, they are opaque in nature. They are not going to allow the thermal radiation to pass through it. They are not going to allow it to transmit through it. So all the objects are or most of the objects are opaque in nature. So due to that, the transmittance will become 0. Now when transmittance becomes 0, so what will happen? There will be only two factors or the two portions of the incident electromagnetic wave. So one will be the one portion will be reflected, one portion will be the absorbed. Now here you can see that reflectance plus absorptance or reflectance plus emissivity is equal to 1. It means that when reflectance will be increasing, suppose reflectance is 0.8 or 0.9, at that time emissivity will become either 0.2 or 0.1. Okay. Similarly, if emissivity is very high like 0.8 or 0.9, at that time reflectance will become very, very low. It means that all the objects which are good reflectors, they will be the poor emitters. Similarly, their emissivity will also be very, very low. And all the objects which are good emitters or good absorbers, they will be very poor emitter. Okay. So one should know about this fundamental concept, so that all the metallic objects, since they are very good reflectors, so metallic objects are having very, very low emissivity. Now we are going to quickly talk about the thermal properties of the terrain. So here we can see that water, rock, soil, vegetation, atmosphere and the human tissues all have the ability to conduct the heat directly through them. That is the thermal conductivity onto another surface and to store heat. So storing the heat, that will be the thermal capacity. Some materials respond to changes in temperature more rapidly or slowly than others, that is the thermal inertia. So mainly we are going to talk about these three properties: thermal conductivity, thermal capacity and the thermal inertia. So these are the basic definitions given. So thermal capacity is the ability of a material to store heat. It is measured as the number of calories required to raise a gram of material 1 degree centigrade. Water has the highest thermal capacity, near to 1. It stores heat very well related to all the other materials. Now when we are talking about the thermal conductivity, that is represented by K, is the rate that heat will pass through a material and is measured as the number of calories that will pass through a 1 centimeter cube of material in 1 second when two opposite phases are maintained at 1 degree centigrade difference in temperature. So the conductivity of material is variable due to the soil moisture and the particle size. Many rocks and soils are extremely poor conductors of heat. So thermal conductivity is mainly talking about the how much conductive your material is, or any material is good conductor or the poor conductor of the thermal heat, that could be measured with the help of the thermal conductivity. Now another is thermal inertia, that is represented by P here. It is measurement of thermal response of material to temperature changes and is measured in calories per square centimeter per second square root per degree Celsius. Now thermal inertia, this is computed by a multiplication of thermal conductivity, square root of multiplication of thermal conductivity, density and the thermal capacity. Now the thermal conductivity and the thermal capacity we have defined previously. Now when we are talking about the thermal inertia, so thermal data set is also used to measure the thermal inertia. But since we do not have the direct measurement or the field truth for the thermal conductivity as well as the thermal capacity of the surface, so we are basically measuring the apparent thermal inertia, and apparent thermal inertia is mainly shown here as 1 minus A divided by delta T, where A is the albedo or reflectance in the visible band of the spectrum, and delta T is showing the difference in the temperature in the night time and the daytime imagery. Now the difference between the maximum and minimum temperature you can measure with the daytime and the nighttime imagery, so that is the delta T. So with the help of and this delta T could be measured with the help of the thermal data set, daytime thermal data set as well as the nighttime thermal data set. You can measure the delta T. After measuring the delta T, one will be able to measure the thermal inertia of the surface. Now here the same formula, apparent thermal inertia will be equals to 1 minus A divided by delta T. Delta T can be derived by subtracting the minimum nighttime temperature from the maximum daytime temperature, and in this two images will be used to calculate this difference in the temperatures. So all the materials which will have the low thermal inertia, they will have high delta T, because here you can see that when delta T temperature difference will be very high, okay, then apparent thermal inertia will be low. When apparent thermal inertia will be low, the object or the feature is going to change the temperature rapidly. When the apparent thermal inertia will be very high, so at that time this delta T will be less. So for those features, what will happen? Those features can hold the heat for a longer time period. That feature will resist to change the temperature, so it can hold the heat for the longer time period. There are different applications of the thermal imagery. So determine the rock types, structure, soil types, soil moisture, forest fire, subsurface fires. Okay, so we can use the thermal imageries in the several applications to find out the temperature information. Now this is the changes in the radiant temperature for 5 surface cover. So 24-hour cycle has been considered here. So here we can see that rock and soil, they will have very high radiant temperature in the daytime imagery. So rock and soil in the aerial thermal data, so also you have seen that buildings and the soil, they are having very high radiant temperature. So they will appear very bright in the imagery. But just after the sunset, there will be rapid change in the temperature. Temperature will go very down. Okay. Now when we will come to the vegetation and the water, so there will not be very much change in the temperature. But if you will do a comparison between vegetation and standing water, so in the night time imagery here you can see that there will be high thermal emission or the radiant temperature detected from the standing water or vegetation, that will have that will be appearing very high, so that they will be appearing bright in the imagery in comparison to all the other features like damp terrain, rock soil and the metallic objects. Okay. Now this is the night time image of the Great Lake. The data set lands at TM band number 6. So here you can see that in night time imagery, so the water is appearing very bright. Why? Because very high thermal emission is detected for these locations. So this is appearing very bright. Okay. Now even here you can see that channels are there, water channels. Okay. So these in these channels also water is appearing as water is detected as very bright features. Now soil and rock near to this lake, they are appearing as very dark, because their thermal inertia will be very low, and so that they will be rapidly changing the temperature. They will be rapidly emitting all the heat at the heat that was absorbed in the daytime, in daytime. Now since water is having high thermal inertia, so this is going to store the heat for the longer time. This will resist to change the temperature, so that in the nighttime imagery also we are going to see high thermal emission, so that finally kinetic the high radiant temperature will be detected for these locations. Now this is the emissivity of certain features like black carbon powder. This will have the emissivity 0.98 to 0.99. Distilled water, this will have the emissivity again from 0.98 to 0.99. Ice will also have very high emissivity 0.97 to 0.98. Plant will also have the emissivity 0.96 to 0.99. Sand will have the emissivity near to 0.93. Now if you are coming to aluminum foil, here what you are going to see that the emissivity is 0.03. Now this is the thermal infrared sensor. So very long list is there. So we are not going in detail of all the sensors, but few sensors we will be talking and we will be discussing in this lecture. So first is INSAT 3D. So INSAT 3D, this was launched in 2013. So the INSAT 3D imager is an improved design of VHRR, very high resolution radiometer, heritage instrument flown on the Kalpana 1 and the INSAT 3 emission. So INSAT 3D carries a multispectral imager, optical radiometer, capable of generating the images of the Earth in the 6 wavelength bands, significant for the meteorological observations, namely visible, shortwave infrared, middle infrared, water vapor, and 2 bands in the thermal infrared region, offering an improved approximately 1 kilometer resolution in the visible for the monitoring of the mesoscale phenomena and the severe local storms. So here if you will see that the visible range, so here quantization bits, this is related to the radiometric property, this is 10 bit. So here if you will see the thermal TIR1, thermal infrared 1 and thermal infrared 2, they are having the resolution approximately of 4 kilometer, here we are going to see, and in the visible the resolution is approximately 1 kilometer. So these are mainly used for the meteorological purpose and mainly for the mainly at the global scale or the national scale, because the resolution is too coarse, so that you cannot use for mapping and monitoring of different cities, thermal properties of different cities or the a small object. Now another sensor is the thermal ASTER thermal infrared data. So ASTER is advanced spacebound thermal emission the reflection radiometer. So here you are going to see the total number of bands are 15, and out of 15 bands, here you are going to see the 5 bands are dedicated for thermal infrared, starting from 8 micrometer to 11 micrometer with a spatial resolution of the 90 meter. So ASTER dataset has also been widely used by the scientific community to do the study of the thermal properties of the terrain. Now we are coming to another sensor, NOVA AVHRR. So this sensor is having coarser resolution and thermal infrared band is 10 band number 4 and 5. These are 10.3 to 11.3 micrometer and 11.5 to 12.5 micrometer. Again, they are having the spatial resolution of 1.1 kilometer coarser resolution, and here this is again used for the study sites at global scale, global or the national scale. Now we are coming to the specification of the Landsat 4 and 5 sensors, because Landsat 4 and 5 optical and thermal, these sensors have been widely used by the scientific community to do the mapping and monitoring of the land use and the land cover. So Landsat 4 and 5, so it is having the 6 band in optical multispectral and 1 band in the thermal. So band number 6 is the thermal band, and here you can see that all the bands, they are having the spatial resolution of the 30 meter, but band number 6 is having the spatial resolution of 120 meter, and this is resampled at 30 meters, so that if one will be interested in overlapping the optical band with the thermal band, so there will not be any pixel mismatch, so that this is resampled at 30 meter pixel size. Now we are coming to the Landsat 7, that is the Enhanced Thematic Mapper Plus, ETM Plus. So here again the spatial resolution is particularly if you compare with Landsat TM, it is higher than the spatial resolution of the Landsat TM, because here you are going to see the 60 meter spatial resolution for the thermal band, and here you can see that and this is resampled at 30 meter pixel size. And band number 8 is the panchromatic band, in which we are going to see we are going to get a high spatial resolution of the 15 meter. Now after that operational Landsat imager OLI and the thermal infrared IIRS, Landsat 8 was launched, in which the operational land imager and the thermal infrared sensors were there. And in this the 2 bands were thermal infrared, and in last few years Landsat 9 has also been launched. So here you can see that band number 10 and band number 11. So these are the thermal bands of the spatial resolution of the 100 meter, and here you can see the number of bands are more in comparison to the previous missions. So thermal infrared, these are 10.6 to 11.09 and 11.5 to 12.5. These two are the thermal bands, band number 10 and band number 11. And 30 meter and these bands are resampled at a 30 meter pixel size. But it is suggested by the agencies that to work with the band number 10. Initially both the bands were used, but now people are using band number 10 only. Now when we will have the thermal data set, so in thermal data set, so data set will be stored or the information will be stored according to the number of bits, or you can say according to the radiometric resolution. Thermal properties will be or the thermal emission will be received by the sensor, and that will be stored in the terms of the pixel number or the digital numbers. So this is the our first task. When we will have the thermal data set, the first task should be to convert the digital number into spectral radiance. Now the conversion of the spectral radiance will use the few information L minimum, L maximum, QDN and the Q max, where L I is the at sensor spectral radiance which we are going to measure, and the L max is the maximum at sensor spectral radiance, and L minimum is the minimum at sensor spectral radiance. So these could be easily measured because they will be represented by the DN values of the pixel, and QDN is representing the DN value of the pixel. Now here you can see that L max for Landsat 5, Landsat 7, Landsat 8, L max and L minimum values, these are given 15.303, and Q max, that will be the maximum pixel value in the imagery. So that could be here seen, like for Landsat 5 it is 255, Landsat 7 255, Landsat 8 65,535. So for band number 10 and band number 11, you can see that values are given, and one will be able to calculate the spectral radiance using these values. Okay, because simply you will have to put, suppose one is working with Landsat 5, so L max will be replaced by 15.303, L minimum will be replaced by 1.238, and the Q max will be replaced by 255, and QDN will be the pixel value, and this formula will be implemented on the entire image, so that we will have one separate image that will be the radiance image or the spectral radiance image. Now when we will have the spectral radiance image, so after that we are going to calculate the at sensor brightness temperature, or we can say that the radiant temperature also. So radiant temperature is measured, it is represented by Ti here. So this will be measured with the help of the spectral radiance, Li, that we measured in the previous step, in which we used this formula, L minimum, L max, L minus, and QDN. With the help of that, Li will be measured. So Li will be given as input here, and K1 and K2 are the constants, basically calibration constants, and this information will be provided by the agencies, or from the user manual it could be obtained, and most of the time in the metadata also you can get the information of the calibration constants. So calibration constants K1, K2 for the Landsat 5, 7 and 8, here you are going to see the values. So K1 and K2 values, you are going to see the difference in the values, you will be able to see. Now these will be given as input in this formula, and Li is already measured. Now when this value will be given, one will be able to calculate the at sensor brightness temperature, or you can say the radiant temperature. Now after measuring the radiant temperature, one will be able to measure the land surface temperature, that is represented by the LST. Now this TB is brightness temperature, or the at sensor temperature, at sensor brightness temperature, or you can say the radiant temperature, that will be given as the input here. And here emissivity, that will have to be measured. So there are several approaches to measure the emissivity of the earth surface or the land use land cover. So people are implementing those algorithms. There are several algorithms. One very famous approach is NDVI based emissivity measurement. So people are also measuring with that NDVI based emissivity measurement, and other algorithms are also available. You can, if one is interested, they can go in detail of the algorithm. Here in this formula we can see that lambda is the wavelength of the emitted radiance, TB is the radiant temperature that has been given as the input, rho will be a constant that will be given as h multiplied by c divided by sigma, where sigma is the Boltzmann constant, h is the Planck's constant, and the c is the velocity or the speed of the light or the speed of the electromagnetic wave. So one will be able to measure the land surface temperature with the help of that. Now this is the land surface temperature image, which is derived from the Landsat data set, and here this temperature was generated by measuring the NDVI based emissivity, and here in this image you can see that there is variation of the temperature from 19 degree to 32 degree. So here dark color, they are showing the very low temperature 19 degree, and 32, all the bright patches, they are showing the 32 degree. So this is the image Landsat data set, which was acquired for the Delhi on 27 February 2009. So one will be able to measure the land surface temperature, as well as if one will be interested, they can also find out the forest fire information, what is the heat or the temperature information. That information could also be retrieved from those data sets. Now I have covered the lecture, and in next few minutes we will be starting the question answer session. Thank you.